So yeah, this is a presentation. There we go. So it's very light. So it's malware. Malware is a good thing to do, read or write, either way. So what to expect? So today we're going to do a rough. I've only got like 20 minutes, 30 minutes, so I will talk quickly, and some of it will be a little bit high level. But effectively, you are here today making sure you're in the right presentation. Sample 78, Deconstruction of the Linux Adversarial Toolkit. Caveat, it appears the little clicker didn't particularly work with my Mac, so I may be backwards and forwards pressing a spacebar, so bear with me. All right, so who am I? Just some guy that likes computers, some random dude and just stumbled up onto stage. If you wanted to know a bit more about me, I won't waste your time. There's some information about me in the scheduled pamphlet, and come chat to me later if you found it interesting, or tell me off, either way. So some things that you probably should have to get some value out of this presentation. So it's imperative you actually know what a computer is. Aside from that, knowing what Linux is probably a good step as well. Being scared of system calls is probably not a very good thing for this presentation. Being able to read a very light amount of assembly is welcome. However, a lot of the stuff that you will be reading is in source code, so it's not too bad. It's important you know what implants and controllers are, and most importantly, you can get over the fact to think that it's only Windows that has malware. Malicious actors do compromise other platforms. That is definitely a thing. All right, so let's go. What to expect inside this presentation. So in the theme of summer nats, expect a full teardown and rebuild of a Linux adversarial in-use implant. It's not like some implant that found on the internet from like 10 years ago, whatever it was. This is an in-use implant. Expect the analysis of the original binary. Expect the re-implementation of the original binary back to source code. And also expect an implementation of a compatible replacement controller. So the controller was never available to me, so I thought, whatever, just write my own. So just quickly, I was going to go back here to who am I? So the only thing I'm going to tell you right here, I need a caveat here, is I am a Queenslander. So we are by all means the most Australian people that live in Australia. So I will try extremely hard to behave myself, but the way I would have said that last dot point in Queenslander would have been, fuck it, I didn't have the controller, so I just wrote it myself. All right, so just please be aware, I will try to behave. Please note this presentation, if it seems light on the details, come see me afterward and we'll have a chat. It was a lot of work that I've pumped into this before I got to slides, and I had to condense this thing into under 30 minutes. So just please keep that in mind if you think it's light, but I can answer any question that you have about the thing under the hood. All right, so second caveat, copyright information. I did not write this implant. The original one is not mine. If there's a person in the audience thinks that it's your implant, I'm cool with that. Put your hand up, yell out. If you're a bit weird about that, happy to come and have a chat with me later. I do have questions. And if you're not weirded out, I did make some bug fixes. So if your organization takes commits upstream, more than happy to make some. I promise I won't include any backdoors to your backdoor, I promise. All right, so promise. All right, so the sample. So this particular sample is one binary within a suite of tools used by an active actor. And when I say active actor, like within the last 6 months. It became an analysis candidate due to the fact that during binary triage, it appeared to have some really novel and interesting features inside it that I figured you may as well dig into this thing and see where this is going to lead. It is a 64-bit ELF binary, so 64-bit ASM, 64-bit Intel platform assembly. And it was built on target using GCC. So that's no indication at all of how new or how recent it was. It's just the particular build was 447, which is circa 2012. Well, that's fine. And we're looking at about 58K of binary. That's what we're looking at. All right, so as far as the analysis component goes, so we've got two parts of this presentation. There's an analysis component, and I've got a small number of slides for reconstruction, but then we just go into a demo, because if we do the analysis, you don't really need to see me do it twice. So as far as the analysis goes, static only. I was only saying to someone the other day when one of my mates, one of my colleagues were having a chat about, oh yeah, dynamic, static, and I'm like, whatever, mate, I like to read the book. I don't like people reading it to me. So I do static analysis. This will be my last IDA Pro project from next week. Unfortunately, I've already installed the JDK onto my machine, And from next week, I will be using exclusively Giuffre. So get on that bandwagon nice and fast. So this is a full reverse engineer, like full software reverse engineer of a sample back to complete source, which is not my typical way to perform analysis. For those that are in the audience, and I'm sure there's lots that do analysis, usually it's fairly surgical. You typically approach analysis of a binary with a subset of questions. And if people request analysis of you, like if that's the kind of business that you're in and you reverse binaries for a living as part of an organization, typically you get really fucked off when people ask you, just tell me what this thing does. Because that is by no means anywhere near providing some kind of app specification for you to do it in a timely fashion. However, in this case, that is exactly what I've done. So I've gone from sample, binary sample, back to complete, pretty close back to complete source. And I was looking at about 50 plus hours of software reverse engineering to do that for a small sample, 58K sample. All right. So as far as analysis goes, there's two things we're going to have a quick talk about. So one, we've got protections and command and control, because they're the most interesting things. Everyone will just leave if we have a chat about how it took me maybe, I don't know, 5-6 hours to reverse their custom argument passing for like argc and argv. That's not very exciting. So protections, so this particular sample had a few novel, low sophistication user mode protections. This binary is user mode. There's no kernel mode component to it. It had some anti-static analysis, some heavily obfuscated strings, the kind of thing you'd expect in a typical sample. We're not going to cover that in the slide or in this presentation. It did have some anti-dynamic analysis, and it also had some anti-forensics as well. So let's hit off on some of those. So I know this might be small for some people to read, but if you can, there is value in there. So the particular binary had a function, which is now back into source code. And this particular function did a few things, mostly for anti-debug. And it would ensure that your ancestry, so your parent process that is calling this process, is what you expect it to be. So at the top there, we have some hard-coded names of expected processes, which include, what have we got, like start proc, k-order-d system. So processes that you would consider to be legal, not anti-debug, or not debuggers, and not processes that may be nasty to your nasty. And on top of that as well, it does another nice thing. So aside from just checking who your parent process is, it also actually does some debugger detection as well. So, and this gets called in various places inside the implant, just to make sure everything is shipshape and things haven't changed as it's performed execution. And there's two different ways this particular function will operate. So it'll either give you a soft exit, so it'll just return with a return code, then you can decide the calling function what to do once this returns, if it says it's found something it's not supposed to be there. Or alternatively, it's got a strict mode where you can exit hard and you just quit out of the environment. And again, this is not, just again to reinforce, this is what was implemented, I just went backwards. So it's none of these things in here are my modifications. So one of the interesting things in here, though, towards the top, you've got a function called ptraceme, or I call ptraceme. And for those people that have done some debugging in Linux, or they've hit anti-debugger stuff in Linux before, you might be familiar with a system called ptrace. So ptrace is what all your typical debuggers use, so GDB, strace, et cetera, et cetera. Ptrace system call, it allows you to be able to debug a process and give control of the process to another process, or alternatively, a tracer can request access to another process. Interesting things about ptrace is that only one process is permitted to be attached, one process is permitted attachment at a time. So you can't have multiple processes actually attaching to your process to debugger at a time. That's significant. Another significant factor as well, in a particular function that was called inside this implant, is that it calls something called ptraceme. So there's a whole lot of different ways you can call ptrace with a whole lot of different requests. This is one. And this is the only particular one that a tracee can call as opposed to a tracer. And if that doesn't work, say for example, someone's already holding your process, it'll return an error code of -1. It didn't work. This is what it looked like in the binary. So if you can see here, if you're not familiar with assembly, that's totally fine, but you'll see it called a ptrace. You'll see the number 1 being loaded into EDX, which is saying call me with the ptraceme option. And if the thing doesn't work, you'll see on the right-hand side, if it's less than what's expected, it'll call exit with a 1. So what that you're seeing there is that if it tries to say, yes, please trace me, whatever it is, and it's already being traced, it will shit itself and quit out. So anti-debug. Novel, small, but does the job. Called in multiple places in the binary. So this particular binary also had an implementation for anti-forensics as well. So Incident responders and forensicators in the audience will be very familiar with the concept of disk analysis or metadata analysis and chronological order of artifacts and timestamp metadata, time metadata, creation, modification times inside file systems. This one here, this implant also had a very novel way to actually deal with that as well and employs an anti-forensic technique which we call time stomping. And what it does here, so this particular function, which again is called in a few different places, what it does is you give the function your destination file that you want to stomp, that you want to change its file time, because you want to move it within your timeline, your chronological order, to sort of throw apart the investigative ability of a forensic analyst. So you give it the destination, but you can also give it a source as well. So it will copy its time and then update its own modification time and its own access time to effectively blend into the environment. So that's exactly what this does here. Using function calls within Linux called stat, so you can call stat on a file in Linux. It will give you its inode information, and inside that inode information, it will have time metadata information in there. So it copies that, and then it uses utime or update time to then write it back to the nasty that you're trying to hide. There is flaws in this. I don't know if the original developer cared or knew, whatever. But the thing is, with using utime, it only actually updates access time and modification time. So there is an anti-forensic flaw in there. Your creation time will remain as it was. Nice to know. All right, so let's move on to command and control. I have no idea how I'm going for time either. All right, let's move on to command and control. So this particular sample, so what made this sample interesting, aside from those few novel techniques for protections, was the way it went about its command and control. It used a novel method that, when you read these things, you're like, oh shit, like, why didn't I think of that? Like, I should have done that, you know what I mean? Like, it's like the person that invented the potato peeler. It's like, that was a good idea. People like to peel stuff, you know what I mean? Like, it's, so, as I said, use a novel method, which is what's highlighted the sample for me to tell you about it today. And aside from the way that it talked to the sample, so the way the unknown controller that we never have a copy of talked to the sample, which is cool. Implementation of the actual implant itself was functionality that you would expect from a typical backdoor or rat. So that's the kind of stuff that's inside the sample. All right, so there's no way you're going to see that, so I'll just talk through it. So effectively, what this sample is doing at a very, very high level, to be able to talk, for the controller to be able to talk to it, typically in a network environment, you've got to, if you've done some socket programming in the past, you've got to listen for a socket. You've got to bind to a port and carry on and fuck around and whatever it is. So in this particular case here, and that's not very good, because if you're on Linux and you just see like a netstat, like what, TLN, it's like, there's something weird listening on there, and I look at the process and I found the badness. So that's, as far as OPSEC, that's not a really amazing thing to do. So I'm assuming there's a few people in the audience that have used Wireshark and stuff before. I'm assuming that's not an unknown concept to some people, and being able to look at a packet capture. For some people that have used Wireshark, I'm sure you've also used it to actually perform packet capture as well. So not just look at someone else's PCAP, actually take your own PCAP. So Wireshark and its command line brother, TCP dump, actually use a library called libpcap. And this implant also does that as well. So what this particular implant does is, instead of doing socket programming, it decides to do libpcap programming, and it writes a filter. So, well, first it listens on the any device. So the any device is using libpcap. It allows you to listen on any of the devices that are actually present on or resident on the machine. That does have a few caveats, because with the any device, so if I was to write this implant, I would not use that, because I reckon that's a really bad way to do it. So if there are some caveats with the any device, is that you can't put it into promiscuous mode. So the IP packets have to be destined for your machine. And if I was trying to do something clever, I would just not do that at all, and just listen and actually look at what the common device is that I want to use, and I would just listen on that device, turn the thing into promiscuous mode, and then I could fire packets to anywhere inside the segment, and I could just task on that. So if you're doing packet capture on some kind of IDS, and I'm not a network guy, so if you know me, you know how much I love ragging on people that do network stuff. So it's so if you're got this new Butte, IDS, IPS, packet capture, layer 2, whatever, it ain't going to do nothing for you, because you're going to see telemetry going to, or tasking going to some random device in the network, and meanwhile your implant's sitting on another host, and it's just sniffing stuff in promiscuous mode. So that's why I would have done it. I wouldn't have done it like this. But anyway, so What it does, it listens to the any device, packets that are destined for it. It then filters those ones out so it only wants TCP. And even though it only wants TCP, it takes any packets on any port. So any packets that come in as TCP'd on the entire port range. And what it does then, it processes those packets. So when you do libpcap programming, you eventually go into this pcap loop, and then you give it a callback function, and you're able to process the pcaps as they come in to do whatever you read them, transform them, do whatever you want. It's very roughly how a very basic like IPS or IDS works, and that's what this does. So it reads the packets coming in on the network, completely skips the whole TCP, completely skips the whole socket program paradigm. So that's great. So what does this callback do? So what this callback does, it actually goes and parses. So again, this is not libpcap code. This is code from the implant. The code goes and parses the data structures and makes sure that the IP is version 4. It goes through and checks some lengths and whatever, some other garbage. So, but then interestingly, it goes on to check that certain flags of your packet are set for tasking to fire. And then if those particular flags are set, it will then go and read the TCP payload, it will process that, and then after that's processed, then it will go and do your execution. So that's the way that works. So, and you'll see in the demo, so I won't keep waffling on. So in a nutshell, so it listens to raw traffic on any device, filters that traffic, checks the presence of the acknowledge and the push internet protocol flags. If it passes that, then it decodes and decrypts the TCP payload, and then it processes and then executes that payload. All right. So control. So what kind of tasks are we looking at? So interestingly, the first thing it does, so this is inside the decrypted payload. So once we're inside the decrypted payload, the first thing it does is it checks a password. That's interesting. Inside the payload itself, which I would deem to actually be a campaign code. It's hard-coded in, written for the individual victim. And then it goes on to check to see if it's one of 7 different tasks. So we have we have this password, then then a colon, and then we have the task string and another colon. And then if the particular task requires arguments to it, an IP address, a string, whatever it is, that all comes after. And then after it's been processed, we hand it to the execution function, and the execution function is what does the business. So, and what this does here, it doesn't do it inside its process, it just forks off a process, does the execution, the parent waits, does its stuff. So in the original sample, so a few interesting things now, like above just the binary itself. But the original sample had 7 tasks, but only 4 of those tasks had accompanying implementations. So even though the binary, the network protocol is geared to at least take 7 that we know of commands, it's only been implemented for 4. I only had 3 in mind because 2 of them were very, very close. So I thought, yeah, whatever, keep going. So of the 3 tasks that were in there that I've implemented, so we've got kbit2, which you give like an IP address and a port, which is another password. So we have a password protected, which is, again, that password's hard-coded into the implant. A reverse shell, and this has no terminal support, which is very, very different to something that you'd expect to use, like SSH that has full PTY support, which is effectively what kbit did. So that's why I sort of mushed them into 2 for the sake of timeliness. It has another command, string command called tacbo, where you can give it a string and it just executes an arbitrary command, but you don't get anything back. It's just a single shot, so you don't get anything back coming back to you, so nothing from standard error or standard out. And also has another command, AIPT, which actually disables the firewall. So if you look back here, you can sort of see up there, you can see like the task number 6, effectively all it's doing is just firing down like an IP tables configuration command for you to accept everything, which is pretty cool. All right, so reconstruction. So the original sample I have re-implemented in ANSI C99. It's pretty much 80% complete. I will finish the rest. The proof of concept controller was written in Python because that is like way faster. And my objective was to ensure that my implant and my controller were interoperable with the original sample, which I can test, and hopefully the unknown controller. That may be useful one day. All right. So some considerations though. So to send tasking to the controller, and we sort of already talked about this before with like socket programming. To send tasking to the controller, you need to transmit the encapsulated traffic, so your encapsulated tasking inside a valid TCP network, encapsulated in TCP protocol. Typically, this requires to connecting to a listening port on the machine. So in this way here. So, as we just said before, we know the way the implant listens for tasking. It hasn't binded to a socket. It's not listening, so how do you connect to this thing? So typically, the way you would go about this is you may say connect to like an existing port. You might do like some kind of a scan of the environment, see what ports are open, and you might connect to say like SSH or whatever, 80, HTTP, whatever it may be. And then even though you're at the application layer, it has no idea what's going on, you just fire this stuff anyway. And that's enough. You've passed enough gates at this point for your implant to know that that the traffic is for it. So even though you're seeing stuff come in on 80, it's actually going to something that's not listening on anything at all right? I thought that was a bit shit. So my controller actually implements its own one-sided skeleton TCP/IP stack. And so what I can do, so just the transmit side, so what I can do, I can just send raw packets to it. I can skip the triple handshake, and I don't need to bind to a port at all. I can just send whatever I want, doesn't matter. All right, let's do a demo. Let's do a demo. I wonder if this is going to work. So I have done live demos in the past. That was a bad idea. So I've got a movie. All right. Okay, so what I've got here, so I've got 2 VMs, do everything in console. I've got an attacker and a victim. Just want to say how awesome Vagrant is. So if you're not a HashiCorp user, become one. It's fantastic. So we have attacker on top and a victim, and I'll talk you through as we go along. Here we go. All right, so just to demonstrate, I'll move this to the side. So just to demonstrate some stuff. So who am I? Whatever, ID, yep, the victim, the attacker, whatever. It's important to prove to you that we're actually on 2 different hosts within the network. So there we go, there's the first one, you see .136. It's fine, sitting on the same subnet, and the victim should be close by, probably next door neighbor. 135, that's fine. It's totally okay to go and break into your neighbor's house. That's exactly what we're going to do. Here we go. So netstat, so just to show you as we go through, what's listening, what's going on. So the only reason I got 80 is because I installed a package just before this. That's awkward. So it's netstat. So it's all we've got there is 22. So SSH. Same for the victim, SSH. So what's next? It's like watching a movie. It's awesome. My son thought this was so wicked. I tried it on him. He thought it was fantastic. All right. So just to prove to you I wrote this thing, so I've got an implant.c, does compile. Here we go. I'm sure lots of people that write C, they're just like, oh, what option comes next on GCC? This takes so long, you know what I mean? Here we go. Implant uses libpcap. The implant's threaded. There we go, so now we have an implant. That's running. Let's see what that does. It runs. But you've got to run it as root. So in the implementation, it actually checks to make sure it is root, which is very important for a few of the features inside the implant. One of them being is that you can't perform packet capture. You can't connect to the raw PF socket unless you're root. It's very important. So it has to be root. It's not an issue. The implant was not about privesc. It wasn't about persistence. You can do that in other ways. That's totally fine. It's a backdoor. So you assume at this point that you've already got root. It's not a big deal. That's fine. All right, so we've run it. Nothing is listening, as we expect. It's listening for packets out of P capture, packet capture. So we've got a controller. Here we go. So I've intentionally put in a typo, just so you know that this is not like machine learning, AI, whatever it is. So it's all right, so here we go. So my controller. So I've got all the particular commands. As I said, the implementation in the implant doesn't support all the commands. So I put that in as well. That's fine. Let's do some stuff. Here we go. So the first one I said, so execute arbitrary commands. So tacbo. That's important. So we do an ls in our home directory. We just got the implant. We don't have anything else. Okay. Didn't want to retop the command, just push up. So let's do that, and let's give it a string, and let's just, I don't know, I'm always touched when people create files. It's very moving. So let's just touch a file on the other person's file system. That's fine. And this is very forensically friendly, telling people that they're owned. It's fine. There we go. Home user folder text. Interesting. So nothing is listening, but it's there. There we go. It just appears. That's pretty cool. That's pretty cool. Pwned. So there we go. So we know our implant's working. That's pretty sweet. Still nothing. That's pretty cool. Still nothing. All right, so something next. So if you've got, say for example, your admin is like doing string searches, like has a really cool cron job where like every 20 seconds he looks for text files that contain pwned. All right, that seems like a fairly reasonable way to do detection. So on top of that, so say for example you continue on, and if you do that, then you just go, oh well, I didn't see any internet connections, so fuck, he must be hitting me over ICMP, whatever. You know what I mean? So it's, I don't know why, but that's just must be. So let's just block all outgoing ICMP. Let's just do that for no particular reason. It just seems like a really fun thing to do. There we go. All right, that's fine. That works. We can list it. There we go. That's done. Drop all ICMP packets. And we'll just ping the machine. There we go, as expected, as expected. All right. So luckily, our implant and our controller have the ability to annihilate someone's firewall. So let's do that. Doesn't need any options this time, just the command. Done. There we go. Out we go. Sucked in, mate. Sucked in. All right. So we've got our last command. So I got 3 out of the 4. 3 and 4 are pretty much the same. As I said, the full implementation of the last one is only differences between how much extra effort was in there to dev for full terminal support. So then you get all the extra nice bits and pieces you get with like line endings and colors and all that kind of stuff. So it was pretty much the same, those session leaders and all the right stuff. But for the sake of this demonstration, this one is fine. So as I said, we still have nothing listening. It's like, it's great. We'd like scribble this file. We'll give them a file. But now let's take a shell on this machine. Let's do that. So our final command for the controller, cabit 2, just to check, there it is, cabit 2, you give it an IP and a port, there we go. And I know there's some people are like, oh wow, Christian's written another shell, why fuck, why did you just use netcat? But it's, and I do actually, in a second, but it's important to know that we've gotten to the point now where we've re-devved an implant and we've actually been able to make a replacement controller for it. So this is talking to like the real stuff. There we go. Ask for a password. There we go. All right, now we've got a connection. Now we've got a connection on port 1337. There it is. All right, so it wants a password. We give it a password. Again, password is the original password that came from the implant. I didn't make it up. Magic syrup. That's what came out of the implant. Highly obfuscated, obviously, but that's what it was. Now we have a shell. What do you first thing you do when you have a shell? Who am I? There we go, root. There we go. We're inside the other box. If you don't believe me, we'll do some LS's. Like ls root. I have no idea why I did that for, but I wasn't going to record my presentation at this point. I was too far in. I was in too deep. Like, whatever. It's fine. It's cool. Here we go. This is the one I was supposed to do. And there it is. There's our file. There's our implant. And if you still don't believe me, I was like, oh, I'm going to exit, but like maybe the audience doesn't believe me. There we go. So it's IP, show the IP address, and come on, type faster. And we're inside our neighbor. We're inside 135. So there we go. Owned using someone's own implant. The best way to do it. All right. So, how are we going for time? The end already. Wow, there you go. Demo. All right. C3 red. Questions? However, I don't take questions because, people either ask me questions where they don't really want to know the answer, they just want to tell me the answer. So I'm not going to do that. That's a waste of my time. And the one question that everyone always wants to ask at this point is like, oh, sweet, so you found this implant, Christian was really interesting, don't really give a shit about talk about C, because I'm like, oh, I found some really, really cool compiler optimizations, let's have a chat about that and how many less cycles it takes. People are like, no, I'm not interested about that. I want to know where the binary came from. I want to know about attribution, that's what I want to know about. So, as we saw, the password, so this is I don't do attribution for a living, so this is just observations that I've made along my travels, and I will let you decide for yourself. All right, so the password was Magic Sarap. That's a thing. So Google is an awesome way to do attribution. You just put shit into Google and attribution comes out, all right? So Magic Sarap is a thing made by Magi. So the reverse shell password is a popular seasoning made in the Philippines. It's a bit interesting. And the tasking strings were all likely derived from Cebuano, which is a very popular language spoken in the Philippines. Cabit is actually roughly translated to the word attach, so that's our shell, attached to the machine. Tacbo is run as an exercise, but yeah, run commands. So, and there was also another set of strings inside this binary, which I'm not going to share today, but that were overtly declaring the actor was Philippine, politically motivated. But I don't know, Philippines have a sophisticated CNE program? Probably not. Psychops? Misinformation? Probably. All right, so in my spare time, which I don't have much of, I like to read blogs, watch presentations. At home, I work from home. I don't particularly like, I work in a cyber shed, which is a converted carport. And I don't particularly like going a lot of places, so I watch most of my presentation stuff in the cyber shed. You can always find me in the cyber shed. All right, so it's, so as a result, I don't really go to many conferences anymore. Used to, a bit over that. So, I watch people's prezos. So in December, FireEye had their Cyber Defense Summit. And they got really excited. People get really excited when they talk about actors you don't see very often. Platinum in this case. They got up on stage and carry on about, yeah, we found Platinum and we've done some attribution and whatever. Microsoft's reported about it, it's been a while, like no one ever sees Platinum. All right, and true to their word, so I've given you guys a little bit more than most people give you. But true to most InfoSec presentations, they give you sweet FA. Like you're hunting, I think I've seen this presentation maybe about 40 times now, trying to derive intelligence from the slides or from what they say, trying to write Yara SIGs or whatever I can get out of this thing, I've tried to well and truly squeeze blood from this stone. And we have the slide here. So there's a particular sample that they've found. So this is a Windows sample, it's not a Linux sample. Particular sample that they've seen that they've happily attributed to Platinum. And they talk about this password thing. So it's not in the slide, but when the guy's actually talking, he actually says campaign password. I'm like, oh, that's a bit interesting. That's a bit interesting, all right. And if you look here as far as the format goes, so this is actually inside, again, like when they talk about, this is actually inside their payload. So this is inside their malicious actor payload, their implants, whatever. So it's encrypted, and you've got this password and a colon and more stuff that they don't tell you about, just to try and lead you on inside their slide. And if you remember, when we went back to what my process text looks like, we have something that I call a campaign code, and its format is pretty much identical to that one. So anyway, it's a light lead. I got a little bit more reversing to do. I got some of the crypt to finish. That's usually a good indication. But I don't know. No one's ever said that they've spotted a Platinum Linux sample. That's pretty sweet. But stay tuned. There we go. Any real questions?